Hello, everyone. Can you hear me?
Yep.
Okay, okay, okay. So I skimmed through the minute paper and someone commented that um, there was some confusion in the gain. So I'll go through that. Um, the gain relationship with the directivity. So I will go through that as well. Let me connect my iPad. Okay. So and at the end we will do the problem solving, okay, which are assigned in the homework. Okay, so we did this, that's fine. Okay, so we were talking about the gain. So what is the gain and how is this different than the directivity? It's actually I think the same thing that it says. Oops. Okay. So it's actually the same thing that it says, like directivity, that radiation intensity divided by power into 4 pi. The difference is that it is now talking about input power or accepted power, right? In directivity, we were talking about uh, radiated power. So, as we have developed previously, the relationship between them, that radiated power is actually equal to the radiation efficiency multiplied by input power. So, whatever input you are giving to the antenna, it is not necessary that the same input power will radiate. Okay. So, there is some losses in between. There are some losses in between. And to tackle that, we are saying that P rad is equal to ECD, that is radiation efficiency, multiplied by P in. So when you multiply this thing here, if I just do it here, um, so it will become P rad into ECD, because if I replace this thing here, right, which will make it ECD directivity, because this is the formula of directivity. So that's how gain and directivity are related to each other. Okay. So gain is nothing but just the efficiency multiplied by directivity. It means that gain has the losses which directivity was not addressing previously. Similarly, if I go down, told that, okay, now we have the gain, but we did not address the reflection coefficient in it, or the losses due to reflection coefficient in it. So we said that realized gain has the losses due to reflection coefficient. Okay. So that's what we were talking about. And I will solve an example for you. Yes, Andrew, go ahead.
Yes, my question is, if you go up on the slide,
Mhm.
and you were saying that the difference between the two relationships is that one uses the, would it be RMS power? And the other one uses the average power?
No, I am saying that gain is the total power we are talking about, but directivity is just including the radiated power. That's why the relationship between them is that in the gain we are incorporating the losses.
So one has the magnitude of the power, the other one does not.
Okay, let's think about it. So what I'm trying to say is that, let's say you have an ideal scenario, right? In which you have an ideal antenna in which there are no losses. So in that case, your gain and directivity will be equal, right?
Right.
Okay. But once you have a practical scenario where there are losses, then your radiated power, like the power that is radiated, or that is what you should say is useful, is not equal to your total power or input power. So it's not, we are not restricting it towards RMS or whole power, but we are just saying that it's just total power we are talking about. So it could be RMS, it could be any power, but it's just that if we incorporate the losses, it will become gain.
Understood. So by getting gain, you have to give up some other form of energy.
Yes.
That would be
Or you can say the
increasing
gain is
give
more
up more
practical.
energy and power, right?
Yes, I think you can say the gain is more practical than directivity because it has losses. Because in real world, there are losses, right? So we should take them into account. Okay. I am solving an example. I think it will help. So this is example 2.10, in which we are talking about that a dipole antenna with input impedance of 73 ohm is connected to a transmission line whose characteristic impedance is 50 ohms. So we need to find a realized gain, okay? So the question is, another thing it mentioned is a lossless half wavelength dipole antenna. So what this lossless means, you will see that too. With input impedance of 73 ohms. Okay, is connected to the transmission. So you can see that from the book, it's okay. Line whose characteristic impedance is 50 ohms. So these two impedances are not matched, right? 73 and 50. They are two different impedances. So they have given the pattern of the antenna. They said that if the pattern of the antenna is sine cube theta, then find realized gain. Okay, so you know that to find realized gain, if you just first figure out what realized gain is. Right? So what we should find in this case to find realized gain. So what are the quantities that we should know to find realized gain?
The radiated power.
Yes, and
The radiation efficiency and also the reflection coefficient.
yes. So these three things we will try to find, right? Another thing is that our maximum intensity is 1 at theta is equals to pi by 2. So we can think about that too. So because they said maximum realized gain, so we can just take the maximum radiation intensity, which will be B naught at theta is equals to 90. And yes. Okay, so let's do it. So if I just try to find P rad first. As they have not given any angles. So we will put just a full angle here. So this will be 2 pi. Right? And when you solve it, it should give you, and there was, sorry, B naught as well. So I think I am not solving the integral, and it should give me B naught 3 pi squared by 4. Okay. So from there, I can find the maximum directivity. So my focus is to find this, 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 and this. So because this quantity is maximum, so this is here, and P rad is B naught 3 pi squared by 4. Okay, so if I move up and I say D naught, which is the maximum directivity, it will be So we got the maximum directivity. We are good. Okay. Now, what I will do, I will see what is ECD. Okay. So because they have mentioned that the antenna is lossless, so in lossless antenna, your ECD is equals to 1. So we are good with that. Okay, next. What this means actually, that your maximum gain is actually equal to D naught, which is equal to D naught. So your gain is actually equals to D naught. And this is a linear quantity. So when you are trying to find the dBs, you will do this. And this is log 10. So that will become, because this is 1.697. So this will become 1.697 2.297 dB. Okay, yes. Now we will come to the, what you should say, the reflection coefficient part, okay? So let's see. So this is not the gain we were asked. This is just we found it, but do you think that the gain that they ask us is realized gain, and that has the reflection coefficient in it? So let's find out reflection coefficient first. So because we know that reflection coefficient is this, and if you, I will come back to that, but I just want to talk about this thing. So if you are given that your antenna dipole has input impedance of 73 ohm and is connected to the transmission line of 50 ohms, okay? So it means that we are saying that this is 73 ohms, Z in, and this is Z naught is 50 ohms. So when we will try to find it, we will do this. And I don't know what it is. It's 123, 23 by 123, something like that. So our reflection efficiency will be 0.965. So either you can find your maximum realized gain as this, that will become 1.6376. So if you deal in dBs, you will add them. But if you are dealing with the linear quantity, you will multiply them. And you can then convert the whole quantity into dBs later. Are we clear about this? Shane, do you think it's fine?
Yeah, I understand this.
Okay, sounds
Doc-
good.
I'm sorry,
Yes,
Doctor. Can you scroll
yes,
up
yes.
fast when you were solving PRAD? Should the bounds be switched for theta and phi, since theta should go from pi to 0 instead of 2 pi to 0?
Okay, so yes. So what happens is, I mean, you can switch them all the time before you are solving them, right? But we know that the maximum quantities we are taking is 0 to pi and 0 to 2 pi, right? So what I have done here, I said that, okay, I can just write it the other way too. It's okay. So I just said that, okay, because I need to solve this, the theta one. So I just get rid of phi first. Is that your question?
Okay, that makes sense.
Yeah. So I just assume that if I get rid of phi first, that will be 2 pi because it doesn't have any other phi dependency in the like the problem. Okay. So now I am just introducing 2 or 3 more quantities. So one is beam efficiency. So we talk about radiation efficiency, we talk about reflection efficiency. So this is another quantity that is called beam efficiency. So beam efficiency is something that talks about the major lobe, okay? So it actually judge the quality of transmitting and receiving antenna is the beam efficiency. Okay, how it judges the quality? It actually, let's say, for an antenna with its major lobe directed along z-axis, that is theta is equals to 0, beam efficiency can be defined as so we are talking about the efficiency that is contained or the like the power that is contained in the major lobe, okay, divided by the total power. So we are saying that it is power transmitted or received within cone angle theta 1. So what this means, we will talk about it. Divided by power transmitted or received by the antenna. So by the, like the power transmitted by whole of antenna and power transmitted or received by only the cone. So mathematically, how you define it is, so you say, instead of pi, you say theta 1. And the other things will remain same. So basically what you are saying, power transmitted or received by a certain angle, like not certain angle, the collection of certain angles is the beam efficiency. So this theta 1 could be anything. It could be the angle of half power beam width. It could be the angle of first null beam width. Depending upon that, your beam efficiency varies. So if we choose that this theta 1 is your first null point, means that you are talking about beam efficiency in this region over the power in the total area, then this will indicate that you are talking about beam efficiency in a major loop. So if I just quickly show you a slide that may a little bit clears the point. That's what we are saying here, that your theta 1 could be anything, right? So if it is this here, this is half power beam width, but if it is first null beam width, then it's the major, it's saying the beam efficiency is the power radiated in the major lobe divided by the total power. Okay. So this beam efficiency is very important for radio astronomy or the antennas where you need to send the signal far away. Like in satellites, where you have to send the signal far away, you do not want your beam efficiency to be less. So that's why you want to have them a very large beam efficiency. So let's say sometimes we need them to have a 90% beam efficiency, which means that the most of the power is contained in that lobe, because we want power to be transmitted so far away that we want beam efficiency to be very high for certain applications. Okay. Now I want to talk about another thing, that is bandwidth. Yes, Andrew? Did you raise a hand? Okay. Okay, so bandwidth. What comes in your mind when you think about bandwidth? Parker? for Eric.
Like the range of frequencies that are available for transmission.
Yes, yes. So right now we know that there are many parameters we have defined as a antenna's characteristics, right? So there is gain, directivity, radiation pattern, and I actually defined reflection coefficient, VSWR. So there are many parameters. So bandwidth of anything is that if we say that certain parameter behave certain threshold for this range of frequency, right? So that that will be the bandwidth of that parameter. Let's say if we say impedance bandwidth, okay? So impedance bandwidth is that your antenna behaves below certain threshold for your antenna's impedance will be below a certain threshold for this range of frequency, right? So that will be impedance bandwidth. For pattern bandwidth, your antenna's radiation pattern should behave according to some threshold for that range of frequency. That will be your pattern bandwidth. So bandwidths are different types of bandwidths, but the general term of the bandwidth is, so what we say, the bandwidth of an antenna is defined as the range of frequencies within which the performance of antenna with respect to some characteristics. So these characteristics, as I have mentioned, that could be pattern, that could be radiation pattern, anything conforms to a specific standard. So let's say what standard I have defined for, now we have defined for impedance bandwidth, or yes, impedance bandwidth was for the reflection coefficient. When we were seeing in the design block, we said that if our antenna is, we said that if our antenna's reflection coefficient is less than minus 10 dB, that is our threshold, right? That's what we have said. So let's say this is your antenna. This is your antenna's reflection coefficient that we were seeing in case of dipole, right? And we said that this was 75 megahertz, right? But what are these frequencies where it was crossing the threshold, right? So these frequency, let's say that was 73 and that was 76. Let's say that. Okay. So these range of frequencies are the impedance bandwidth where your impedance is matched, right? So I can say that your impedance bandwidth is 76 minus 73, which is 3 megahertz. So when you, I think, like listen all the time, we are talking on this bandwidth, right? On radio. So they are talking about range of frequency where they are operating. Similarly, I think if you buy a Wi-Fi antenna, normally Wi-Fi antennas not have the large bandwidth, but some antennas have very large bandwidth nowadays, like the 5Gs, they have some 500 megahertz or more than that bandwidth. So more bandwidth you have, normally when they talk about bandwidth, they are talking about impedance bandwidth. But bandwidth is not just restricted to impedance bandwidth, it could be any bandwidth. Okay, right? Okay, so another term they define in industry is that broadband antennas. So broadband antennas are very, very wideband antennas. So their bandwidths exist in gigahertz. So when they say broadband antenna, if they say that this broadband antenna is 10:1, right? Its ratio of the bandwidth is 10:1. So it means that its upper frequency is 10 times more than its lower frequency. Means that if lower frequency is 1 gigahertz and upper frequency is 10 gigahertz, so it means that the ratio is 10:1. Means the total bandwidth, impedance bandwidth the antenna has was 10 gigahertz, which is very, very large. So 10 is not defining the upper frequency, but it is defining the ratio it has with the lower frequency. So it could be 2 gigahertz and 2 into 10, 20 gigahertz, right? So that could be the range of the, that could be the ratio of the bandwidth. Then we have a narrow band antenna. So what is a narrow band antenna? Narrow band antennas have very small bandwidths, and their bandwidths are measured in percentage bandwidths. And the percentage bandwidth is F high minus F low by F high plus F low by 2. So the average of the frequencies and the difference in the frequency. So like in this scenario, which we are talking about, our percentage bandwidth is somewhere, I think it should be 2% or something. So whatever it comes here, that is your, let's say it's 2%, that is your percentage bandwidth. Okay. So I will talk about polarization in detail in the next lecture, but I want to show you something that makes a case. Are we done here or should I stay? Fabian, are we good?
Yep.
Okay, then let me share. Okay, so what is polarization? So polarization is certain, way antenna is transmitting, okay? So polarization of the radiated energy varies with the direction of center of antenna, and different parts of the pattern may have different polarizations. So I think Andrew raised this question before, that are we talking about electric field? Are we talking about magnetic field? Are we talking about both of them? So it's that we are taking electric field as a reference and we are talking about this. So in the polarization, we are saying that certain way electric field signals orient is the polarization. We can say that with the magnetic field as well, but we have to take the reference, that way we are saying that. So what polarization is? Polarization of radiated wave is defined as the property of an electromagnetic wave describing the time varying direction and relative magnitude of the electric field vector. So the direction of electric field vector defines the polarization. So there are different types of polarizations. We will talk about them, but we need to think that certain way electric field vector orients itself, transmitting from antenna is the polarization, okay? So there are three types of polarization: linear, circular, elliptical. And what is linear, circular, and elliptical? We will talk about this as well. So CW means clockwise, right-hand circular polarized. CCW means counterclockwise, left-hand circular polarized. Okay. So this is linear polarization. So linear polarization means, or horizontal polarization means, that here your antenna is transmitting, like it transmits electric and magnetic fields both, but we are just taking electric field as a reference, that the electric field orients itself in the x-axis. That's what you can say, right? So it is transmitting itself in the x-axis, and from the other end, it's received by the x-axis. So it's a horizontal polarization. Okay. So this is that, like if your antenna electric field orients itself in the y direction and transmit itself in the y direction, then its polarization or antenna's polarization is vertical polarization. Okay. Remember, we are not talking about any edge. They both are E. They both are different antennas that transmitting. One can be transmitting in that with electric field oriented in X direction. The other can be transmitted with electric field oriented in the Y direction. So they both are called linear polarizations. But what happens sometimes that your electric field vector does not remain the same when it transmits. So it changes in whole 360 degrees. And in that case, it gives you circle polarization. When it happens, when your electric field vector is not totally in one direction, some of it is in Y direction and some of it is in X direction, in that case, your phase rotates as it transmits. We will talk about its mathematics in detail, but I'm just giving the picture that how circular polarization works. So there is circular polarization is hard to achieve, but circular polarization has advantage in it, okay? So what happens is that when you transmit antenna in linear polarization or in vertical or horizontal polarization, your receive antenna should be in the same polarization. Otherwise, your antenna will not be received. It's same as the light. I think you heard about polarized light as well, right? So in the light scenario as well, if you want to receive the light, it should have that polarizer. Similarly, if you want to receive an antenna that is horizontally or vertically polarized, you need to have an antenna that is in the same orientation, right? But in case of circular polarization, you can receive any signal because it has both things in it. So if you have an antenna, if you are having an antenna that is transmitting circular polarized wave, you can receive it with the vertically polarized antenna or horizontally polarized antenna. It has both the components in it. So that's why circular polarization is needed for long distance communication. Like for satellites, they need circular polarization because they don't know what happens in the atmosphere. They say that your antenna's orientation can be changed, electric field can change itself, it can become any orientation. So if it is already circular polarized, your waves orientation will not be much affected, right? So that's why they need the circular polarized waves. Okay, any questions? Are we clear about this? Okay. So that's what I was talking about. So this, in this case, this is not the antenna, it's a polarizer, but I'm just describing that this is behaving exactly as an antenna. So your wave is vertically polarized, but if you have a horizontal polarizer in it, like the antenna that is horizontally polarized, your wave will not be received because it doesn't have a path that can pass its signal. So the signal that will be received will be diminished, or there will be no signal that will be received, or if it is transmitting further as well. But in this case, if you see the circular polarized wave is coming, then you have a horizontal not a vertical polarizer or the vertical antenna, polarized antenna. It actually filtered, or it actually received only vertical polarized wave out of circular polarized wave. Then if it is transmitting, the wave is only the vertical polarized and it cannot be received by the horizontal polarized antenna. Is it clear, Michael? Michael Relio?
Mhm. That's good.
Okay. So one more thing I want to talk is that, let's say this is your satellite antenna that is transmitting towards the International Space Station. That's what I was talking, that it can change its polarization. So this is a polarization control. When you change the polarization, the electric field is changing its orientation. And that can happen all the time in space. So we need to cater that, okay? So that's why people like most of the companies want to use a circular polarized antenna for satellite communication. You can have the reconfigurable antennas as well that can change the polarization for you as you want, okay? Now, this is that we have two antennas like that are pointing towards this International Space Station. One is horizontally polarized and the other is vertically polarized, right? So what is happening here, that if your polarization control is set to receive only horizontally polarized signal, right? Then in that case, this vertically polarized signal will be a cross pole for that. Cross pole is some unwanted polarization that you do not want to receive, okay? You want to say that this cross pole should be minimum. But if you are setting your polarization control to receive the vertical polarized wave, then they both will be copoles. Copoles means the wanted signal that you want to receive, right? So in this way, you can see that it becomes interference for certain polarization, or certain angle, but it's not all the time unwanted signal. So it depends on your polarization control when it becomes unwanted or not. So there are H transponder and V transponders. V transponders are the they have vertically polarized waves. They can receive vertical polarized wave. H transponders they can receive horizontal polarized waves. Is it clear? Okay, so now I will talk about homework problems. Okay, so have you looked on the homework problems? So I think, let me first see that. So there is one thing I want to address is the azimuthal and elevation half power beamwidth. There are two types of beamwidth we talked about. And then there is 2.25 question. I was actually grading your first homework. I actually graded one of it. And then I think my iPod was behaving weirdly, so I stopped it. I will do it soon. So, but I'm just, I will go through the homework, but first you tell me if there is any problem. Do you have any issue?
Can you go over part A for 2.14?
Yes, 2.14 is part A.
Also, could you go over 2.8, like just the explanation how to start about it?
Okay, 2.8. I think 2.8 and 2.14 both are asking about half power beamwidth, right? That's what you are talking about?
For
Or
2.8, I was just confused because the power is 1.5. So I don't know, like, do you want the power to be whole power or do we change it to something? I was just confused about it for 2.8. And also the half power beamwidth question.
okay. So you are saying, I think in 2.8, they have given you E, right? Like the electric field, right?
It says EA is a constant and R is the radial distance.
Yes, but what I'm trying to say that when you will try to find the directivity, you have to convert it to the radiation intensity, right?
Yes.
So radiation intensity is like it can get rid of your R. It does not have the R factor in it. So you just have to square your sine 1.5 theta.
Okay.
Got it? You can ignore E minus JKR over R because your radiation intensity does not have the R factor in it. Okay?
Yeah.
Okay, now I can talk about B part of it because I think that relates to 2.14 as well, but I just want to first talk about it. Okay, so I think we talked about half power beamwidth when we are talking about cause, when the radiation intensities were cause. We did not talk about sines, okay? So I think I will just address this one of the question. Okay. So I think with this thing, in the B part, if you see, let me just get this thing. They are asking about half power beamwidth in degrees, okay? But because this is sine cube theta, let's say, that's why if you think about this, if this is your like angle, this in this case it's an omnidirectional pattern, right? Because it's sine. So when it's omnidirectional pattern, it is making with theta, it is making an angle 90 degrees. When you are having a cos cube theta, let's say, or cos theta, it's a directional pattern. That's why when you were finding half power beamwidth, you were saying that this is just our half power beamwidth. But in this particular case, oh, I'm not sharing my screen. Or can you see my screen? Yes.
We're
Okay.
able to your notes.
Yes. Can you see now? Okay. So what I'm saying is that, so that's why in this particular case, you have to take into account that it's not at the theta is equals to 0, but it is at theta is equals to 90. That's why when you find out the half power beamwidth, you will find like the normal way. You will say that sine theta cube theta h is equals to 0.5. Theta h is equals to sine inverse 0.5 1 by 3. That's the same thing that you will try to find. But now whatever comes, like let's say in this case 52.53 comes, right? Now this is 52.53 at this point, right? Thinking that theta is equals to 0. But if you want to think about this, you have to minus 90 degree minus this thing. When you do that, then you can, your half power beamwidth will be 2 into 90 minus 52.53, means that you want to, what you should say, tackle this scenario. So this happens only when you have omnidirectional patterns in it. Okay. So wherever you are having an omnidirectional pattern, you want to tackle this scenario. That's why you want 90 degree minus this point. That will give you the half power beamwidth here. Okay. Okay, now I'll talk about 2.14. Let's see. So 2.14 is saying, you want me to talk about 2.14a or 2.12a?
2.14a is just having theta and phi as two variables when we're trying to solve for 0.5 for like the half power beamwidth.
Yes, I think this is 2.12a and 2.14a is the approximate directivity, right? So first you need to find 2.12a. 1 minute. Yes, so I will try to solve one of them, okay? So I will solve 2.12a. So 2.12a is saying that you have normalized radiation intensity. That is sine theta, sine phi, okay? And you need to find, so both of them are 0 to theta pi and 0 to phi pi. So just remember that they did not mention phi as 2 pi. So when you will find it, you are talking about this area, only, because here your your theta varying 0 to pi and your phi varying 0 to pi as well. So you are talking about this area. Okay. Now you are saying, they are saying that u is equal to sine theta sine phi, as we know that again there is only sine, which means that this is an omnidirectional pattern. You can find radiation intensity, it's fine, but when we are talking about half power beamwidths, so azimuth and elevation. So if you think about azimuth, you want to have cut, right? So azimuth, you want to have this cut or this cut. So both of, in this case, both of the curves are such that, 1 minute. So let's say we are talking about first theta is equals to 90, then your, this thing becomes sine phi, and then you can equate it 0.5, and phi will become 0.5. Sine inverse half power point, and that is actually for, yes, so that is 30 degrees because it is at 90 scenario, so that will become, so that is your azimuth half power beamwidth. But if you want to talk about elevation, again, you will see that at which point your, this thing will becomes 1. So this is, let's say, so it will become phi is equals to 90. Your, this thing will be sine theta is equals to 0.5. Theta is equals to sine inverse 0.5. And again, 30 degrees. And your phi h will be 120 degrees. So for the both azimuth and elevation, you will have the same half power beamwidth, but it's not the case for all of it. Like, let's say you are talking about, yeah, I think for E, it's also the same, but for C or B, it's not the same because it has sine theta different than sine square phi. But in both cases, you will put theta or phi where you are getting the value as a maximum. I want to address 2.25 as well. I don't know whether you have done it or not, but 2.25 is talking about electric field, and it's asking you to have cross approximate formula. Find the directivity using cross approximate formula, okay? So let me,
Wait, Dr. Khan, for the elevation, should it be theta n instead of phi n?
yes, good question, 1 minute. For elevation, so when we talk, I all the time mix them. So when we talk about elevation, we thought about theta, right? 1 minute, let me confirm. Is there? Let me. They are used so much interchangeably. So azimuth is horizontal all the time, right? Azimuth is horizontal and elevation is vertical. Or it's the other way around. 1 minute.
I think that's right.
Yes, azimuth is theta is equals to pi by 2. So what I did? I think I did fine. Azimuth is theta is equals to pi by 2, and elevation is phi is equals to this. So I think that's fine.
Oh, I meant for the elevation. So for azimuth, we're solving for phi n, but for elevation, we're solving for theta n, right?
Yes.
Okay.
Another thing is that because in this scenario, what we are talking about in this scenario, so elevation is fine. Elevation is normal because we are saying theta is equals to pi by 2. That is this thing, like this scenario. Cutting like the horizontal thing, right? But for elevation, when we are talking about this scenario, normally we were cutting it at phi is equals to 0. But here we are cutting it at phi is equals to pi by 2 because our maximum thing lies only here because we are talking about only this region. So that's why we are cutting it at phi is equals to pi by 2 because this is your phi is equals to 0 and here your phi is equals to pi by 2. Does this make sense? Right? Got it? I myself confused about azimuth and elevation, but I feel that this is right, that azimuth is the horizontal cut and elevation is the vertical cut. Okay. So 2.25, I was saying, okay. So 2.25 asks you the maximum directivity, like not the approximate directivity. And for that directivity, you have to have the beam widths. So I want to just say maybe that 2.25 says that E max or E is actually cos pi by 4 cos theta minus 1 E minus jkr by r. So because you have to use the cross approximate formula, which is d naught is equals to, and because it is using the maximum directivity, which is d naught is equal to 4 pi 1r 2r, right? So in this case, you need to find these beam widths. And beam width you can find by finding E max. So E max, when you find E max, you just try to find the maximum value. So you can get rid of R and you can just say that. So it should be 1. So it has cos in it, which suggests that what it is. I mean, what type of pattern is this? Is it omnidirectional or is it directional?
Directional.
it's directional. So in that case, when you will find half power beamwidth, you do not have to do 90 minus something. The half power beamwidth is a true half power beamwidth. So in this case, because this is E and not intensity, so it will be not 1/2, but it will be 1 over a square root of 2. And then you can just
Where did the 1 over square root of 2 come from?
So for half power beamwidth, normally when you have U, you do, let's say U is sine theta, you put it at half power point, right?
Yeah.
For half power beamwidth. But
Yeah.
because this is E, that's why it should be 1 over square root of 2.
Okay, just the form. All right.
Okay. So this is pi by 4, cos theta, maybe this is half power point. And then you have cos theta h1, and you can say h is equals to cos inverse one. Okay, is it fine? There is something wrong here. 1 minute, I did. Pi by 4. No. Okay. So this is like pi by 4, 4 by pi, and this is cos theta h minus 1. This is already 1. So this is cos theta h2. Okay. And then this is cos inverse 2 and theta h. Because when you will finding this inverse, this could be plus and minus here. So you can add or subtract. So it could be cos inverse 2, or it could be cos theta h is equals to 0. So theta h is equals to cos inverse 0 or cos inverse 2. So because we don't know what is cos inverse 2, so our cos inverse 0 is theta h is equals to 90 degree. So that's what, and your half power point is 2 into 90. That is 180 degrees. Okay. Any other question? And 1 minute, what question numbers were there? 2.32 is easy because it's just asking you to take care of certain losses. So it's easy, it's fine. But 2.25 we tackle, 2.14 and 2.12 are similar. 2.8 is fine, and then 2.4. 2.4 is just dealing with cos, so it will be direct half power beamwidth, it's fine. And 2.3 is also, it's fine. But do you have any other question you can ask? We can go through that as well, or we are good?
Professor, a quick question.
Mm-hmm.
In the situation where it's pi over 4 plus or minus pi over 4, in a situation where that might be non-negative versus multiplied by positive, So you come up with a negative, therefore the -1 becomes +1. In that situation, say they were both negative or both positive, and you have 0, so you have a homogeneous relationship. What effect does that have on the energy produced?
Mm, maybe I'm not getting. So why you are saying we are having homogeneous relationship? Because of cause?
When it was plus or minus pi/4, the only
Yes.
reason that it was 1 and 2 was because it was -1 times or negative pi/4 times 4/pi. So that gave you
Yes.
1, right?
Yeah. Hmm.
So negative and negative is positive. So you start off with +1 instead of what could have been 0 if it was both the same signs being multiplied by each other. So then that would turn that to 0 and it would turn the second section to 1. So having that shift, what effect does that have on the overall relationship of the value of theta in terms of our energy? Is it related to U is sine h of theta? Because that value of theta will go in to determine the energy.
Um, I think when you have the cause, right, then um,
It's 90 degrees to the sine.
yes. But what we were talking about is that when you have a cause, you actually have a pattern that is directed towards theta is equals to 0, right? And when you have a sine, you have an energy pattern that is directed towards theta is equals to 90. That's separate scenario. But you are talking about this thing that when you have plus and minus, you are saying that you likely to have two patterns. That's what your question is?
Right. I was saying if it wasn't negative pi/4 times 4/pi, it wouldn't have been -1.
Yes,
So if
but
it
here
was,
in this scenario, it's just the mathematics, right? So we are likely to get two values, these two values, but this does not exist. So that's why we pick that one that is real.
right, it's kind of like quadratic. It's the one that you
Yes. So
determine
that's
is
why we just said that, okay, this is not real. So we
right.
will pick the other one.
Okay, so the effect of the fact that we started out with 1 equals cos theta h minus 1 instead of 0 equals cos theta h minus 1. Say pi/4 on the right hand side had been negative.
This
And when you
we
multiply it
started
by-
because it's given in the book. So it's not that we did not produce it by ourselves.
Right, no, I understand. It's the way that I stated it. All I was asking is if the left hand side of the equation is 0, so 0 equals pi/4 times the argument of cosine of theta h minus 1, the effect that that would have on the overall value is non-relevant because we determined that series to be non-real, but that's only because that was 1. If it were 0, wouldn't that change the outcome?
If this was 0,
Yes.
of course, it will change. If this would be 0, then you have nothing, but you will have cos theta h minus 1 is equals to 0. And then your cos theta h is equals to 1. And then you have cos inverse 1, right? So that will change the whole scenario. Yeah.
Right. So all I'm saying is that in that very simple step, it could get you confused. It seems like.
Yeah. Yeah,
So
that's right.
trying to tie it to what the representation is That's why I asked about energy. If what effect that value has on energy, it
Yes.
can make sure that you didn't make a mistake somewhere and added something when you should have subtracted.
Yeah, just think about that. You do not want to um, have a half power beam width that is outside the range that you are supposed to give, right? So that's why whatever thing you find should be in the range. Like it should not be something that if you are given 0 to pi and 0 to pi by 2 and your half power beam width comes out of that. So that doesn't make sense. So you should be within the range.
But if that were 0, the section that we said was not real would become real, and the section would have no effect, because the one where we had 2 on the left-hand side was the one that was determined to be real, correct?
Yeah, I think we can talk about this more.
That's fine.
Yes. So any other questions regarding the homework? Are we good? Okay, then